All right, so here's our AP Calc ABBC review session. So this is hosted by North Creek High School's Math Club, but it's on behalf of me. So let's get here quickly. So first, we're going to go through the exam format. We'll go through that very quickly. Then, honestly, I have the AP Calc CED. I put that in my slide deck, so that shouldn't be. We shouldn't spend way too much on that. After that, we'll go through all the content required. Since most of you guys here are AB, we'll just go through the AB stuff. Maybe BC later. We could go through some BC topics, but that's only if BC people come, if more BC people come to this session. And then after content review, I can do a live practice quiz. So you can like see me do a practice quiz, look at my thought process and how I'm doing the questions. And then, or we could do a practice AP Calc FRQ on, what's that called? I was about to say Google Classroom. I meant College Board. So we could also do that as well. And then if we have any time, or if you have any questions immediately, then you can ask me through chat, or you can also just unmute and ask questions there. So let's get started. First, we have limits. So what is a limit? A limit is basically when you're approaching something, right? And they exist when the left-hand side limit is equal to the right-hand side limit. So yeah, let me get a graph actually. So honestly, this here's how this is going to work. It's going to be very intuitive. Here, I'm just going to pull up my Desmos. I'm just going to graph something. I can't present one way, but okay. Let's just say we had y or f of x equal to x squared. I just want to show what a limit is, right? So if we zoom in very close, so here it's x equals 2. It's like over here, we see that from the left-hand side, it approaches 4, and from the right-hand side, it approaches 4. So they both approach the same thing. So then therefore the limit exists. But like, let's say what if, okay, x is less than 3. Does this work? Oh yeah, okay, perfect. Then f of x. I'm just gonna make another example very quickly. 2x minus 6, sure. And then say we have x is less than 3. So here, the limit as x approaches 3 does not exist because from the left-hand side, it approaches 0. And from the right-hand side, it approaches, oh, actually, it's not defined there. It doesn't need to be defined, and we'll look at this later. But they're not approaching the same area, so therefore the limit doesn't exist. All right, let's go back to the slideshow. So, therefore, okay, where was I? So, oh yeah, big point is functions don't have to necessarily be continuous. You can have a hole right in the center. I should probably exit out of this again. And then where's my Desmos? Right there. There we go. So let's just say, am I allowed to do this? Oh, perfect. So here I created this very weird scenario where at x equals 3. So if I approach 3, let's say where's 3? Oh, is there no 3? If I go to 3, yeah, at 3 it's undefined. So technically that spot is undefined, but the limit still exists because the left-hand side approaches the right-hand side, they're the same. So it doesn't have to be continuous in order for the limit to exist. All right. And then here's like some ways to solve limits. So first what you do is you try plugging in values. If that doesn't work, then you can do 2 different ways. One is multiplied by the conjugate. And what a conjugate is basically you take it's positive. So let's say you have a plus b, and then you multiply by a minus b. So for example, a perfect example would be number 8 over here on the slide deck. What you can do is multiply the top and bottom. Or actually, first what you should try to do is plug in values, right? So if you plug in -3 into here, you'll see that the top and bottom go to 0 and 0. And if you see like a square root or something like that, then you can multiply by its conjugate. So then you could be multiplying by here, let me just, oh, perfect. I can just have this whiteboard right here, and then I can just write very clearly. So I do not want to do that. Come on. There we go. So here, so if this is our limit right there, then what we can do for the limit as x equals -3, what we can do is we can multiply the top and bottom by the plus instead of the minus. The conjugate is basically the opposite. So instead of subtracting 4, we'll be adding 4 right here. -4. So then if you evaluate that, then you'll see that the top, what is it? It'll go to, this is just a difference of squares. So it's just a squared minus b squared. So then that would just be 2x plus 22, because these are, square roots, right? So square roots, when you multiply them to each other, you get rid of the square root. Minus 16, and then you have this thing right here. 2x plus 22 minus 4. And then you can plug in 3 into there as well. So then what is that? That would be 0, right? That would be 0. Oh wait, you have to be multiplying by 4 there. No, but you get the idea. The idea is that you have to be multiplying by the conjugate. I don't want to waste too much time on that, but that's just one idea. Another idea that you can use for limits is you can also use L'Hopital's rule, and we'll look at that later. It's when the top and the bottom, if they go to 0 over 0 or infinity over infinity, then what you can do is you can take the derivative of the top and the bottom. So then through that, then you can also try evaluating the limit as well. And over here on number 9, for example, right, if we take the limit to infinity, so let's just say the limit as x approaches infinity of x plus 8 over 2 square root of square plus 8. In order to do this, what we need to do is you need to look at the dominating terms, because the biggest terms, that's what's going to take over the integrals, or I'm going to call this an integral. It'll take over the limit. So like think of it like x cubed plus like x, right? So it's like if x was equal to 1,000, then what is it? X cubed would be like 1 with 9 zeros, right? That would be 1 trillion. And then x 1,000 is like barely anything compared to like 1 trillion. So the x cubed in this case would be dominating, or that's what leads to the asymptotes. That's what what do you say? Like it directs motion, I would say. So over here, like the dominating term here is x, and over here we have the dominating term is the square root of 2x, or okay, here we have limit of negative infinity actually. So let's just say we have a limit to negative infinity. So what does negative infinity does? If you put this, it becomes positive, right? So then we have this negative 2x squared. So if you put infinity there, that's just going to lead to a positive right over here. And negative infinity right here. So let's just think of it as negative infinity over square root of 2 of positive infinity, right? But then these two have the same power technically, and because the square root of x squared is basically x, right? So then now we can just take just 1 over the square root of -2. And that's the answer to this limit right here. I might have overcomplicated this a bit too much, but just look at dominating terms and then just take those. And then if they have the same power, then you just do the division. It's just 1 over √2. Well, here, when we're going to negative infinity, then it'll be negative over here at the top. But you have the square root x squared, then that'll be positive over here. So that's limit to infinity right there. Does anyone have any questions so far? All right, we'll just move on to the next slide. So another topic in terms of limits that we have to discuss is continuity. And continuity has 3 conditions. 1, f of a is defined. So if you go back to, let's go Desmos right here. Let's go to this thing right here. Actually, I think this is a better way to explain. So f of x equals x squared. Let's say at x equals 2 right here. So it's continuous right there because it's defined at that point. The limit of the left side equals the limit of the right side, and the limit equals that defined point. So there's three different conditions here. So one, it's defined at this point right there, 2 or 4. Two, the left-hand side limit is equal to the right-hand side limit. And three, the limit itself is equal to the defined point right there. So that's what it means for a function to be continuous. So I think it's a good idea to remember those three conditions. Go back to, yeah. So just remember those three conditions for continuity and you'll be set. All right, here is the squeeze theorem, which is not really covered too much. It was in the unit 1, the CEV, but basically it was saying if f of x, g of x, and h of x have this relationship where f is bigger than g, which is bigger than h, right? And then at a, f of x, and h of x are the same value, L, right? That means if f of x is the biggest and LA, oh my God, I keep like, but if you have f of x is the greatest and h of x is the smallest, right? And they both approach this L value and g is in the middle of f and h, then g of x must also be L because it's squeezed in basically. Think of this position over here. F of x and h of x are squeezing g of x at L. So if f of x is the biggest and it's at L, and h of x is the smallest and it's also at L, at the specific a value, then g of x, which is in the middle of f and h, must also be L as well. So this is the squeeze theorem right here. Not super important, doesn't really come up on the AP exam a lot, but it's definitely good to know. And finally, finally, we have the intermediate value theorem, which states that if you have an interval in f that's closed that is continuous, therefore, let me just read this right there. The intermediate value theorem states that if f be a continuous function over a closed interval a to b, which is domain having values f of a and f of b at the endpoints of the interval, then the function takes any values between the values f of a and f of b at a point inside the interval. So it's basically saying if you have an interval, let's say, okay, let me bring up the whiteboard back again. So let's say you have an interval of 2 to 5, right? And let's just say, and this interval is continuous, right? Or yeah, so let's just say we have f of x is continuous in this interval right here. And let's say you have f of 2 is equal to 4 and f of 5 is equal to 10. That means between 2 and 5, that means you must have y coordinates between 4 and 10. That's what the intermediate value theorem is stating. So like when you have the word intermediate, it's just like what's in the mediary, what's intermediate between 4 and 10. So between 2 and 5, you're going to have y values of 4 and 10. That's what this statement is trying to say. So that's the intermediate value theorem right there. And that is unit 1, basically just limits and continuity. Not really tested that much on the EP exam, but the reason why you study limits is because limits define the derivative. It's what's up right next. So here is differentiation. Now, before talking about what the derivative actually is, we should clarify what the average rate of change is. And average rate of change is just the slope. It's literally just the slope. It's the change in output divided by the change in input, which is the change in y over the change in x, right? So now average rate of change is between 2 points, right? But then what if we bring those 2 points like together so close to each other that it almost becomes 1 point? That's where we get the idea of the instantaneous rate of change, which is the slope at an infinitesimally small change in input, or what we call dx. Like dx, think of a change of x that's super, super tiny, right? So over here, we have the change in output for the smallest change in input, which is the derivative. Right over here, we see this picture. So this is d dx of y. So it's dy is the smallest possible change of y over the smallest possible change of x. Or yeah, so let's say in the smallest possible change of x, y is changing 4. That's what like the derivative is trying to say. So here is the definition of the derivative. This might not look super familiar. Let me write it on my whiteboard again. Let's clear all of this right here. So we have f prime of x. This is another way you can just say f of x plus h minus f of x over h. Now, what does this represent? This is basically just slope. So over here, let's say we have a point f comma f of x, right? And another point, right, is x plus h. Let's say this is h distance away, right? So between point 1 and point 2, it's h distance away. So then now this is h plus x. Yeah, it's x plus h, and then the output would be f of x plus h. You're putting this input into this output function, and you get f of x plus h, right? So then now the slope between these 2 points, right, is just the change in y over the change in x, which is f of x plus h minus f of x over, which is an x plus h minus x. And then over here, you just see that the x's cancel each other out. So then what you're left with is h, right? So now, actually, I forgot one more thing. You need to put in the limit as h approaches 0. Because over here, in order to find the derivative, we're trying to bring these 2 points as close to each other. So h is 0. So the distance between those 2 points are 0. And that is the definition of the derivative right over there. And this doesn't come up on the exam a lot as well, but it's definitely good to know. And then over here, definition of derivative of point C, that's like the alternate form of the derivative. Again, this is just basically a slope formula. You just need to understand that derivatives are just slopes. And if you can interrelate the two formulas together, you're good to go. Over here, I've said that kinky points are not differentiable. And what am I trying to say here? Basically, in order for something to be differentiable, you need the point to be continuous, first of all. So I have the same conditions over here. The point needs to be defined. If the point does not exist, then you can't be taking the derivative of the slope of it, right? So it has to be defined. I mean, the limit has to exist and the limit has to equal a, right? So it has to be continuous. These are the conditions for continuous. So everything that's differentiable is continuous. Keep that in mind. But then the left-hand side derivative must equal the right-hand side of the derivative. So over here in the not differentiable spot, we see that the derivative of the left-hand side is negative, but the derivative of the right-hand side is positive. So the derivative of the different sides are not the same, so therefore it is not differentiable. That's what causes this kinky point here. Whereas over here on the left-hand side, where we see the slope at that point, the left-hand side derivative and the right-hand side derivative equal the same, the limits of them at least. All right, so then now here we get to the fun part. This is where you have all these derivative rules over here. So first of all, the derivative of a constant is 0. Just think about it. A constant does not change, and derivatives measure change. And if there is no change in the output whatsoever with the same input, the derivative is going to be 0. Power. Here we have x to the power of n. Now, basically what you do is you take the power, you multiply it, and then you multiply to like x, right? So you have n times x, and then you subtract the power by 1. That is the power rule, very self-explanatory. Product rule is when you have, you take the derivative of 1, so you have f prime of x multiplied by the normal of the other, g prime, and then add it, then you like flip it around. So it's f prime g plus g prime f. So that is also fairly self-explanatory. I could explain why this works the way it works, but like I think this one is super easy to understand. Quotient rule, there is a really nice way to memorize it, and I'll bring so let's just say that we have the numerator right here. We have it high and we have it low, right? So then the derivative of this is going to be low d high minus high. No, I'm getting it wrong. My bad. It's high d low. Sorry, my bad. High d low minus low d high. No, okay. Now I'm just screwing this up. My bad. So I'm just gonna say top derivative of top times bottom minus derivative of bottom times top over bottom squared. Oh yeah, bottom squared. There we go. But there is another fascinating way to think about it. So let's just say you had f of x over g of x, right? You had f of x over g of x. Now, if you want to take the derivative of this, you can actually be pretty smart about it. And you can say, okay, well, over g of x, that's basically saying f of x times 1 over g of x, right? And what do we have here? We have a product. With this, you can basically do the product. Pretty fascinating. So then you just take the derivative of this multiplied by 1 over gx, and then you add it to the derivative of 1 over gx times f of x. And then you add those together, and you should get the same thing as this right here, this chunk right over here. But I think if you can find a way to memorize the quotient rule, that would be beneficial. And then one more thing, I think we'll talk about this in a later unit, and it's the chain rule. I'll explain that in a later unit because we'll take too much time there. Here are the derivatives of trig functions. A good way to remember them is all the derivatives with co in them. So cosine, cosecant, cotangent, all of those are negative. So derivative of cosine is negative sine, derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. So you have all those negatives over there, and then anything else that's not the co or like cosecant cotangent, those are positives. Sine and cosine are a definite must to remember. Tangent also, I think, is fairly easy to remember. I think on the right hand side, that's when people start to forget. I just like to think tangent and secant are interconnected, but tangent has secant squared and secant has secant tangent. Then cosecant and cotangent are related to each other. So try your best to memorize this for the AP exam. Yeah, I think it will be very beneficial to, like, especially if you're given like secant for like find derivative at that moment, then it will be very useful to do that there. Other special derivatives to know is the derivative of the natural log is 1 over x, and the derivative of e to the x is e to the x. It's a very special function, one of my favorite functions. But yeah, those are very important ones to know for the AP exam. All right, so then now we are at unit 3. So at unit 3, it's basically, now we're implementing chain rule. And here, let me find a way to explain chain rule. I think it'll be very beneficial. So, okay, don't we agree? So like y over x versus y equals 2 over x. The rate of change is double. Is double for this compared to this. So this one grows twice as fast. So we would expect it to have twice the slope, right? In order to reach that twice the amount, right? So then now similarly, let's just say we had y is equal to x cubed versus, or actually this, we can do better than that. We'll say y is equal to x plus 1 cubed versus y is equal to 2x plus 2. Right? So here, 2x plus 2, that grows twice as much as this one over here, which means that the rate of change must be twice as much. So then here, we have, what is it? We just do our normal power rule, right? But then over here, when we do dy dx, this is going to be 3 times 2x2 squared, right? But then this itself, right? This grows twice as much as this. So it makes sense to multiply this by 2. That's how I think about chain rule. I think it's a very useful way to think about it, and like why chain rule works the way it works. But like basically this is what I did, right? I just took, this is our inner function, and then outer function is this entire thing. The outer function, I took the derivative of that first, and then the inner function is like, oh, it grows twice as much as it would normally would, right? So then here I took the derivative of this and then multiply that out. And that's how chain rule works. So no need to memorize this gibberish right over here. So basically just take the derivative of the outer function and the inner function just stays, then multiply by the derivative of the inner function, and you keep on doing it. It's a chain essentially. If you have multiple outer and inner functions, then you do it again and again and again. All right. And then implicit differentiation is just basically chain rule if you really think about it, except now you're dealing with other variables. So for example, over here we have this 2y cubed. So if you were to do the chain rule over here, right? It'll be 3 will bring out, so it'll be -6 and it'll be y squared. So it'll be -6y squared, but then y is its own variable, and that grows differently from x. So then we need to take into account how y grows with respect to x. So then therefore we need to multiply dy over dx. So that's what implicit differentiation basically is. And implicit differentiation is pretty nice in the sense that you have a dy dx over here, and then you can like isolate everything and then solve for dy dx. It can be very helpful in specific situations. All right, so here in unit 3, we're trying to find derivatives with all of these different types of rules, and you've got to figure out which one to use for which. Power rule, that's like your number one. You try to find that. Product rules, whenever you have two things multiplied to each other and you want to get the product, you want to take the derivative of a product and use product rule. Similarly, if you see like numerator over denominator, then you use quotient rule. If you see nested functions, so something inside of something, then you use the chain rule. And then if you see x's and y's, like you see in the previous slide, all together as one, then you do implicit differentiation. And then there's also the talk about higher order derivatives. So it's basically what is a second derivative, what is a third derivative, and so on and so forth. And we're going to talk about this later, but the second derivative is the derivative of the first derivative. So the relationship between the second derivative and the first derivative is similar to the relationship of the first derivative and your so-called normal function. So that's a key distinction. So the slope of the first derivative is the second derivative. Like the slope of the normal function is the first derivative. So then we see those relationships between each other, and then we can connect them. And that's how we can apply it to multiple different contexts of calculus. All right, so now speaking about context and contextual applications of differentiation. Now we're like digging in on what the derivative truly means, and we're going to put this in specific context. So derivatives is the instantaneous change of one variable in comparison to another variable. So you have dy over dx. It's the change in y over the change in x, over the smallest change. That's the instantaneous. Now you have dy or like dr dt with the dr over dt, right? Which is dr, which is the change in r over the change in t, right? It's the smallest change in r over the smallest change in t. So that's what the derivative truly represents. And one particular way AP likes to involve applications is 1D motion. So there's three things you need to know. And if you've taken physics, then you will know position, velocity, and acceleration. Position is where something is in comparison to another object. So let's say I have my phone over here and I have my water bottle over here. That would be, let's say it's like 5 centimeters away from each other. So the water bottle is 5 centimeters away from the phone, right? That is a position. That's you're putting something in context of where something is. Velocity is how fast an object travels in the direction of travel. So basically you need to know velocities are vectors. They can be negative. Usually speeds are not negative. You can't say like, oh, I'm going -3 miles an hour, but you're saying that with respect to direction, that makes complete sense. And then acceleration is how fast something is speeding up or something is slowing down. So yeah, so if something is like speeding up, then we have, then the velocity and the acceleration have the same side, and the acceleration is causing the velocity to go faster. But then if the velocity and acceleration have opposite sign, then it's slowing down. So it's like the acceleration's wanting to resist motion and wants it to go the other way. Essentially, that's what acceleration does. And if you know physics and how forces work, I think it'll make a lot more sense as to why the same signs of velocity and acceleration means it's speeding up, and opposite sides of velocity and acceleration mean it's slowing down. Oh yeah, I did say that they're vectors, so that's good to know. And in terms of calculus, the derivative of position with respect to time, where AKA the change in position versus time, is a velocity. Think about it like miles per hour. Miles represents a change in position, and then time is time, change in position over time, that's our speedometer, our speed, or in this case would be velocity. And similarly, a change in velocity over time, like how fast something is changing, right? Then that would be acceleration right over there. All right, now here's related rates. And this is probably one of the most hated topics out of all like AE students. So here, what I've done is I've created a solution or like a pathway to solve related rates problems. So first, you need to define what represents what in the problem. Let's say you have a volume. Let's bring back this. Let's say you have a volume. So let's say you're dealing with a sphere. It doesn't really matter what's in the problem. So say, okay, this is volume, and then this is the radius, right? Then what you do is you take that formula, and then with that formula, you differentiate it with implicit differentiation. see rates, right? And rates are with respect to time. So you want to take the derivative with respect to time of all of this. So then here, that would just be dv dt on the left-hand side. On the right-hand side, what we do, we take chain rule, right? So first we take the derivative with r, right? And then what is this power rule? So it'll be 4 pi r, and then we subtract the power by 1. And then now r is changing on its own terms, and t is changing on its own terms. So we have to make a connection between the two. Like, okay, now it's dr over dt, right? So yeah, that's how we do this over here. And then now we have a thing given. So let's just say that the volume is changing at like 8 cubic feet per minute. Right? That would be perfect. Like volumes in cubic feet per minute, right? And then let's say when the radius is 4, how is the radius changing, right? So now we can just plug in information. So you just say 8's over here, and you put 4 is right over here, and then you can solve for dr dt, right? And then you just divide by 4 pi right here, 16, and then 4 pi. And then now you have this right over here. So always start with the formula, do implicit differentiation, plug in what you know, and you'll get the answer. So that is how you do related rates. And sometimes the hardest part with related rates is actually coming up with the formula. Actually, let me bring up my thing back again. So a lot of the times with related rates, you have like a ladder or something, right? And something, it moves like this, and it moves like that, and all that stuff, and you have a bunch of rates. Well, the key thing you got to notice is ladders, right? They have a horizontal and a vertical component, and they're sliding around that. So then now you can just use our quote unquote formula, a squared plus b squared equals c squared, and then you take that with respect to time. So now it'd be that I think this would be, yeah, because some of these are stationary. For example, c is constant, right? So c, that derivative of that would be 0. But a and b, they're not constant because it's let's say if ladder is falling this way and falling downwards, right? So a and b are not constant. So then there'll be 2a dt plus 2b 2b equals 0. And then you plug in whatever you know and you solve something. So sometimes you got to be very clever with how you create these situations over here. But that's that. Let us move on. Okay, tangent line approximations. Okay, this is another like application of derivatives. And this is not too bad for AB students generally. First, you have like a slope with a specific x value. So you need to find the slope and you need a point. And once you have those two information, you can put that in slope point form. And that's it, you're pretty much done there. So if you're given like y equals something, or what you have to do is you have to find a way to figure out the slope. And then you got to plug in points. So to give you an x value, you also need to figure out the y value as well. Then you put this into this equation right here, the slope point form. Hopefully you should memorize this and understand how this works as well. This is basically just slope intercept form. It's actually pretty neat on how this works. Actually kind of crazy how this works. But yeah, just plug in all the information to this, you got your tangent line approximation. Oh yeah, we were talking about L'Hopital's rule. It's basically when you're taking a limit and the bottom and the top are 0. Then what you can do is you can take the derivative of the numerator and the denominator, and then you can just evaluate the limit again. So you have a redo essentially. And then only when something is like infinity over 0 or like 0 over infinity, we can't really deal with that. We'll just say that's undefined in terms of AB calc AB. But if you have 0 over 0, take the derivative of the top, take the derivative of the bottom, and do it all over again, and you should be good to go for there. All right, now we're at the analytical applications of differentiation. So here comes our other two theorems that we need to know for AB calc AB. So I'm thinking intermediate value theorem. That's like you need to know the intermediary. So if you have 2 points, like you have 2 points with an x interval, then all the points within the y intervals, they would exist within the x interval. That's what the intermediate value theorem represents. Then the mean value theorem over here, saying if f is continuous from a to b inclusive and differentiable from a to b exclusive, then there is a point C where the derivative is equal to the slope between a and b. And for that, I don't think so. It's really easy to understand without a graph. So over here, let's just say, okay, straight lines are pretty useless. Let's just say we have random curves, right? And let's say we have point A and we have point B, right? So this theorem is saying if this is continuous from A to B and it's differentiable from A to B as well. I mean, it's continuous from the closed interval and differentiable from the open interval, right? That means for the average rate of change right here from A to B, there's going to be some other point C. Let's say it's right here, where the slope is exactly the same as the slope from A to B. So it's basically saying f prime of C. So let's just say this function is f. That means f prime of C, so the derivative of C is equal to the slope between A and B. And that's just basically f of B minus f of A. This is a change in output over the change in input, which is B minus A. So this is what IROC, this instantaneous rate of change, equals AROC. That's this theorem right over here. So that's the mean value theorem. Besides the mean value theorem, we can also talk about the extreme value theorem. And for extreme value theorem, I like to think about extrema. And extrema is basically minimums, maximums, and all that information as well. So here, the extreme value theorem saying if f is continuous from A to B, then there's at least one maximum and one minimum on the interval. So that makes sense, right? So let's say we have, yeah, again, we can just use this interval right over here. Like over here, we have one maximum and one minimum over here. It has to just be, it just has to be continuous up there. And honestly, it's kind of pointless theorem. The theorems that we use the most is mean value theorem number one, intermediate value theorem number two. I've never seen extreme value theorem used that much, but I guess it's good to know. Let's move on. All right, over here, I have three graphs, f of x, f prime of x, and f double prime of x. So what we're going to do is we're going to analyze these graphs over here. So let's say as x approaches 0, f of x, right? We see that the slope, it went too far. The slope over here is positive, right? So that means our f prime graph that represents the slope of f of x should be positive as we approach 0, which we see right over here. All right, and as we go away from 0, right? We go away from 0, we still see that the slope is positive, right? And over here, as we go away from 0, we go towards the positive side, we see on f prime that the slope is still 0. Now, let's talk about how the slope is changing. So the slope is positive, but as we're approaching 0 from the left-hand side, the slope is getting closer and closer to 0. On f prime, we see that the velocity, I'm just going to call it velocity. You can think about a velocity, or you think about the derivative, is approaching 0, which means that the slope at x equals 0 is approaching 0. So this 0 means that the slope of f of x equals 0. As you can see right over there, the slope is 0. And then as we go away from 0, x becomes positive, then we see the slope increasing, right? The slope goes from 0, goes to 1, goes to 2, and it increases, right? And similarly, we see that the f prime graph also has increasing, says that, okay, at x equals, I actually don't know what this value is right there, but x is going away, that the slope of f of x is getting bigger and bigger and bigger. And then why do I have f double prime over here? So over here, we see that f of x, the slope is increasing, right? Or actually, the slope is positive. I should be careful. The slope is positive, but the slope is decreasing. It's going from some, let's just say this is 5 over here. Let's just say it's like 2 over here, and it's going to 0. So the slope is decreasing. And as you see over here, you can also see that the slope, the value of the slope of f prime is decreasing, right? So over here, f double prime, which is the derivative of f prime, shows that, okay, on f prime, you see the slope of f prime is negative over here. And we see that there is a negative slope over here. We have -6, -4, -2 as x approaches 0. The f double prime shows that the slope of f prime is negative. However, when we go away from 0, as x becomes positive, then slope becomes positive f prime. So f double prime, the slope of f prime, becomes positive. But there's another thing that there's another connection that we can bring between f of x and f double prime, right? Here, the slope of f of x is positive, but it's going at a decreasing rate. If that's the case, then over here we see that it's going concave down. That means over here, whenever f double prime is negative, that means its slope is increasing at a decreasing rate, and therefore we'll call it concave down shape. However, let's say f double prime is positive, right? That means the slope is increasing at an increasing rate. So here we see f prime is increasing, right? It will be positive. That means, and f prime is also increasing as well. So then f of x will be increasing at an increasing rate. And therefore, when f double prime is greater than 0, f of x will be concave up. Okay, I spent way too much time on these graphs, so I'm just going to move on to over here. So when f prime is greater than 0, that means the slope of f of x is greater than 0, which means f of x itself is increasing, right? I'm just going to show it by thing with my camera. I don't know if you can see me, but it's going to be increasing. And similarly, when f prime is less than 0, the slope of f of x is negative. And when the slope is negative, f of x is decreasing. When f double prime is greater than 0, that means the f prime is increasing. So like how we see f prime, the relationship between f prime and f is similar to the relationship between f double prime and f prime, right? So f double prime is greater than 0 and f prime is increasing. That means the slope of the slope of f of x is increasing. So it'll be increasing at an increasing rate, so therefore it'll be concave up. Conversely, let's say we have f double prime is less than 0. That means f prime is decreasing. So like one above, one order above, that would be decreasing. That means it'll be increasing or decreasing at a decreasing rate, therefore causing the concave down shape. All right. I mean, these relations are super important. That's why I'm spending a lot of time on that. You need to understand how it works. I don't know how I conveyed my message there, but it's very important for derivative calculus. Okay, maximums and minimums. So here, f of x is at a maximum when f prime is equal to 0 and changes from negative to positive. So let me just pull up right here. So in order, let's just show a picture of maximum, right? A maximum is right over there. The derivative of the maximum, right, is 0. And more importantly, for it to be a maximum, right, the slope goes from positive slope to a negative slope. So honestly, you don't have to like remember this. You can just draw it and you'd be like, okay, the derivative is 0 and the slope changes from positive to negative. That's what defines a maximum. Similarly, a minimum right there also has the slope of 0 and the slope changes from negative to positive. But there's also another thing that you can mention over here. So with over here, when you go from positive to negative slope, notice how this graph is concave down, right? That means f double prime is less than 0. And over here for a minimum, it's going from negative to positive, which means it's concave up. So therefore, f double prime is greater than 0. So that's how you determine minimums and maximums. And this is what this slide basically says over. It's the same thing. Okay, this is the candidate test to find mins and maxes. So basically, minimums and maximums of any interval can occur at either when f of x is equal to 0 or f of x is equal to undefined. Those are called critical points. And also you can find minimums and maximums at the endpoints. So let's just say you had an interval from here all the way to here, right? So let's just say this is like x is equal to 3 and x is equal to 5. Over here, like there's like no f prime, there's not equal to 0 anyway. There's no like 0 slope here. Or actually, okay, let's just say it like dips down, like so there's not really a slope to 0. Then what we have to look at the endpoint right over here. So over here, you see like, okay, x equals 3 is at its maximum. This is the maximum of the interval. So you also have to check endpoints as well. Where did don't know where that is unfortunate. Let me pull it up real quickly. We are right here. There we go. So then you got to check either the critical points or the endpoints, and you got to check all of them to make sure you find the maxes of the range. All right. I think we're basically done with unit 5. Now we're talking about unit 6. And basically this is integration, and integration is the opposite of the derivative. It's basically, instead of finding the slope, now we're going to find the area. You got to understand derivatives and areas are the opposite. So like accumulation of change is the rate under the rate graph. So like let's say you have miles per hour is a slope, right? Miles per hour is a slope, and then you have hours, which is on the x-axis, right? So if you multiply the rate, which is like the height of the graph, multiplied by the x-axis, like if you see, if you do like miles conversion, not miles conversion, unit conversion, you just see you get miles, right? So then you're just going the reverse direction of derivatives, essentially. And over here, it says the unit for the area of a region defined by the rate of change is the unit for the rate of change multiplied by the unit for the independent variable. So you're just multiplying the height of the graph multiplied by the independent variable, and that gives you the change of a specific quantity. And we'll talk more about that later. So over here, we have Riemann sums. So here, I just want to say this is a left Riemann sum, this is a right Riemann sum, this is a trapezoidal sum, and this is a midpoint sum. So basically what you have to do is you got to find these intervals, right? And you got to multiply these by each of these heights, and then you add them all together. That gives you a representation of the area. So over here, you got to be careful. So left Riemann sums, when the function is increasing, if you just draw it out, you'll be like, okay, it gives you under-representation. But if you have a right Riemann sum and it's increasing, then it'll give you an over approximation. And then trapezoidal sums are usually like the most accurate just because they fit in to the points more nicely. So there's that. And then midpoint sums, you don't really see that much. Oh yeah, if the function is decreasing, then left Riemann sums will be an over approximate and right Riemann sums will be an under approximate. Just keep that in mind. All right, so here, there's the Riemann sum, how Riemann sums are connected to integrals. And honestly, this derivative thing, sorry, this sum thing is really whack. I would not recommend like reviewing this at all, but it's there if you want to know what this is, but I'm not going to go through it. So basically what integrals are is basically Riemann sums of infinitesimally small widths added up together, and that gives you the sum of the area of the curve, right? If you just make those widths as small as possible and you make so many of those rectangles together, eventually you'll get the area of the curve. And that's what the integral represents. And indefinite integrals just basically represent the function that represents area. I had a boo-boo in the spelling over there. And definite integrals represent the area of curve between 2 points. And sometimes you can find the integral by just looking under the graph. You don't necessarily need a function to integrate, or you can use integration techniques to find the integral. And now here is the fundamental theorem of calculus. The integral from a to b of f of x dx is basically you take the antiderivative and then you just subtract the top minus the bottom value. And this is pretty important because a lot of times you take the integral and be like, okay, what integrals represent accumulation of change, right? So you're changing. So like, let's say the integral of velocity is a change in position. But if you don't have an initial position to start with, then you can't figure out the final position, right? Because that's how final position, in order to figure that out, you get the change in position, but you need the initial position as well. So the initial plus the change equals the final, right? So you got to remember that integrals find the change between something. And if you want to find the final state, then you need to find the initial state as well. So you got to be very careful in terms of, what integrals truly mean. It represents a change in a value of something. Okay, yeah, and also, yeah, very important. I mean, if you take the antiderivative or the integral or something, then you need to add c, because any constant, right? Any constant, when you take the derivative of f of x plus c back again, it becomes 0. So you can have any constant attached onto here, and it'll equal to the same derivative, right? So you got to be very careful. So don't forget your plus c whenever you're doing indefinite. All right, now here are integration techniques that I'm going to be talking about here. So first of all is u substitution. How I would recognize u substitution is I see like x cubed and 3x squared. Automatically, my brain is thinking, all right. Here I know 3x squared is the derivative of u cubed. So then probably I'm going to use u cubed as u and then 3x squared as du. So that's like what my trigger in order to do u substitution. So here I see u squared and then make sure I set my u and du correctly, and then I just integrate all. Integration by long division. I don't think so. AB really covers this, but it does definitely come up on the exam. I remember on the mock exam, there was one particular question like this. Basically, you just got to go back to your pre-calc knowledge and divide this integral. So over here, what is it? You have this integral, and how you determine this is you have like some random long like polynomial divided by a small polynomial, and then you just divide, and then you have this function over here, and then you just integrate each individual part. So x, that will become x squared over 2. 3 will become 3x, right? And then you have this remainder part, and then you leave it at that. Integration by parts, this is specifically a BC topic. Remember that this is ultraviolet voodoo. You got to set something as u, something as dv, and you got to find du and v. And then you put it all into this ultraviolet voodoo right here. And sometimes you got to do it multiple times in order to get the answer. So don't forget that that exists. A lot, because I think the biggest thing with integration by parts is people know how to do it, they just forget to do it on the exam. So you got to be careful. Remember, integration by parts exists. Tic-tac-toe method, it's on here. It's honestly not super important, so I've skipped this. Integration by linear partial fractions. This is also only on the BC exam, but basically what you do is you can split it up into 2 parts. And since no one is BC in here, I'm not going to spend too much time, but you can split like this thing into fractions, and then you can take the integral of that. And also this is improper integrals. Like so we have integrals to infinity. What you need to do is you need to make those integrals just have a limit. Those limits go to infinity. Then you just evaluate the integral normally. And then you have like this 1 over infinity thing. Technically, you're not supposed to do this, not supposed to write it. Just you have to say that the limit of this just equals 0, because 1 over infinity, as something goes to infinity, if the denominator gets super, super large, then the overall quantity just becomes like 0. So that's improper integrals right there. Not super difficult as well. You just need to evaluate normally and then you see, okay, does infinity make it go super big, super small? And you figure that out. If you come to an actual answer, then it converges. Otherwise, it diverges. Okay, unit 7. Here's now AB decides to take this weird turn and decides to shift over to differential equations. Basically, there's just equations with derivatives in them. And sometimes what you have to do is you have to verify solutions to these things right here. For example, let's say you had y squared plus 2y prime plus y equals 0. Then it'll give you a bunch of answer choices. And with those answer choices, you just take the derivative of the answer choices, you plug them into the equation, and if it works, that's the right answer choice. That's basically what it is. Here, also in differential equations, there's slope fields, and with slope fields, they're pretty self-explanatory. Basically, the lines represent the slope at that particular point. And with slope field questions, I'll look out for places where the slope is 0, note the x-coordinate and y-coordinates of those, and then try to plug them into like answer choices. It's like a multiple choice question. Yeah, here you can see like at all the same x values at different y's at all the same x values, it has the same slope. So that means the slope field is dependent on x, not on y. If you saw the entire row like have the same slope, then the slope field is entirely dependent on y, not on x. Good to keep in mind there. Euler's method, this is basically BC, but essentially what you can do is take dy dx, right? You have a and b, you have this initial condition. What you do is you find the derivative, and like you can extend the derivative on. So we just draw this real quickly. So derivatives represent slopes, right? But like so derivatives represent slopes, and we have this really small part over here. Then if we know that we're changing x by a specific amount, then we also know, all right, we know that the change in y over the change in x, right? That's approximately dy over dx. So if we alter this slightly, then it could be like the change in y is approximately dy dx times the change in x. So if we figure out the derivative of something, let's say it's 4, and we're changing this by 0.5, approximately y is going to be changing by 2. So that's how you have the rise over run in order for it to be 4. So And then you just add on to y, and then you do that multiple times. That's how Euler method works. Separation of variables is another important key aspect. This is common. Yeah, I guess this comes in differential equations. But essentially what you do is you have this dy over dx over here. So you put all the y's on one side, all the x's on one side, then you integrate dy, integrate dx, and then based on that, you're able to find a solution. That's what separation of variables basically is. And you can only do separation of variables if it's just multiplication and division. If you're adding dy and dx together, it doesn't. Because you need to make sure you separate it, and you can't necessarily separate it without doing a bunch of nasty math. So just for AB, just you have to be able to multiply and divide, and that should work that way. Okay, exponential growth, exponential models with differential equations. So here we have the exponential growth and decay model right over here, which is basically it's saying that the rate is proportional to the amount. So dy over dt is equal to ky. So if you have 100 over something, that means the rate is going to be greater than if you had 50 or something. So what this directly displays over here is exponential growth. Actually, let's just do this equation. So we have dy over dt is equal to ky, right? So then, if you want to do separation by variables, you can just put all the things like y onto one side. So you do dy over y is equal to k dt. Then what you can do is you can take the integral on both sides. So you have basically integral 1 over y dy equal to the integral of k dt. K is a constant, it's just a proportionality constant. So then you can just put k on the outside, right? So then we have k over here. Then dt over here. All right. And now we've learned before that the derivative of natural log is 1 over x. That means the derivative of 1 over x, the integral of 1 over x, because they're opposites, has to be natural log of x. Here would be a natural log of y, but there's a special case because natural log can only be positive, it can't be negative. So we have to make sure we take the absolute value of y. And over here we have kt plus c. So then now what we have to do is we have the natural log of y is equal to this. If you know how natural logs work, right? This is the natural log of a equal to b. That's basically saying that e to the b is equal to a, right? So it's like, what exponent do you raise something to in order to get a? So here this is saying e to the b power is equal to a. So similarly over here we say e to the kt plus c power is equal to y. And this is like just more math over here, but like if you know that a to the power of b plus c is equal to a to the b times a to the c, then you have e to the kt times e to the c is equal to y. But then there's another thing over here, right? E to the c, isn't that just another constant? We have some random constant. The constant to the power of a constant is just another constant. So I'm just going to replace this entire thing with c. So now we have c times e to the power of kt equals y. And this is the function of exponential growth. If you have an amount or a rate that's proportional to the amount, this is the equation that satisfies. It satisfies right over here. So that is differential equation right over here. All right. Where was I? Okay, so then this is just logistics. So then it's basically the same idea, except now there's a carrying capacity. So there's a min and a max. And I think the most important things for logistics is like the halfway point. That's where it goes the fastest. I don't want to go too much into there. Okay, let's go to this final thing over here, because honestly, I don't feel like going through series or polar or vectors right now. It's been a very long review session, so I will finish with Unit 8 and we'll leave it up to any questions. I might just do like a practice run through of an MCQ, or I can do that on my own. I'll just post that later, but let's get through Unit 8 right now. So Unit 8, so this is applications of integration. So it's like we looked at the applications in context of derivatives. Now we're going to look at, right? The first what we have to talk about is the average value of the function. Now, average is basically the sum of something over the number of individual objects. That's what average means in normal context, right? But in integration, average basically means the area under the curve divided by the x interval in which you get that from. That gives you like the average value of the overall function. It's actually pretty cool. So what we have a to b, we take the interval of a to b of f of x dx, and that would be the area under the curve. And then 1 over b minus a, that's like the x interval, right? So you're just taking the area of the function, which is the sum, divided by the number of things in this case, which is the x interval. And that gives you the average value of the function. Now, in terms of in terms of position, velocity, and acceleration, in terms of integration, it's just the other way around, right? Then the integral of velocity is the change in position, which is displacement. And think about the fundamental theorem of calculus, right? That gives you f of b minus f of a. It gives you the change between something. So the integral of velocity, now you have each little velocity multiplied by tiny time. That gives you a change in position, right? And similarly, like a change in acceleration, an acceleration multiplied by a change in time, that will give you a change in velocity. So the integral of acceleration is the change in velocity. And one more thing, the integral of speed, right? For the absolute value of velocity, that doesn't matter about whether you're going in a positive or negative direction, right? If you're going the same direction all the time, then your displacement will be equal to the speed. No, your displacement will be equal to the distance, right? So the integral of speed will be distance there. Okay, so now just finding areas between multiple curves. First thing you do is you need to find like intersection points. So over here, like they have this A and B, so they're able to determine, okay, so this A section is going to be just 0 to 2 of the square root of x squared, square root of x. And then B is basically this square root of x minus this function over here. So from 2 to 4, this is like x plus 2, or sorry, x minus 2. But then they're doing subtraction over here, so it'll be negative x plus 2. So yeah, that's how they figure out b, and then they're just adding those two together, and they get the area over there. So pretty self-explanatory stuff. I have stuff on solids of revolution. Do you guys want to go through that right now, or are you guys calling it a day? Anyone?
We can go through it.
We can go through it. All right.
Yep.
Let me.
Yo, I gotta go now, but thanks for the session, Chendur.
Of course, of course.
Yeah, I gotta go too. Thanks a lot.
Yeah, of
It was
course.
pretty helpful.
Of course. I'll just end the meeting right here because I don't think so. There's too much extra information that I can cover through over here. So